You know, there's a shape that secretly runs so much of our world, showing up everywhere from our test scores to the light from distant stars. It's the bell curve. And in this explainer, we're going to pull back the curtain and figure out why this one simple curve is so, well, universal.
But really, have you ever stopped to wonder why? Why does this one particular symmetrical curve pop up over and over and over again? It can describe your final exam scores, the heights of people in a crowd, even the tiny little errors in measurements of the stars. That's the big question we're diving into today.
So here's our game plan for unraveling this thing. We're going to start simple with the basic one-dimensional curve. Then we'll see what happens when we jump into more dimensions with vectors. After that, we'll uncover its stability superpower, and then get to the absolute heart of the matter, the central limit theorem. And finally, we'll piece it all together to see how it acts as a universal blueprint for randomness.
All right, let's dive right in. Section 1, the simple, iconic bell curve. You've definitely seen this one before.
Okay, so at its core, the standard bell curve is what's called a probability density function. Now, that sounds super technical, right? But all it really means is that it tells us the odds of any random outcome happening. The most likely result is right there in the middle, at the peak. And that elegant little formula you see? Well, that's what defines the perfect curve for every other possibility. But of course, not all bell curves are created equal. The really cool part is that we can describe any of them with just two numbers. The first one is the mean, that Greek letter mu, which just tells us where the center of the peak is. The second is the variance, or sigma squared, and that tells us how spread out the curve is. You know, is it tall and skinny or short and wide? And here is a rule that is absolutely non-negotiable. No matter how you stretch it or shift it, the total area under that curve is always exactly 1. It has to be. That represents 100% of all the possible outcomes, which is, a pretty fundamental rule in probability. So, now that we've got the basics down, let's expand our thinking a bit in Section 2. We're about to take this simple concept and make the leap into the wild world of multiple dimensions. So here's the jump. That one-dimensional curve we were just talking about, that describes a single random number. Easy enough. But now we can talk about something called a random vector. Just picture a single point floating around in some high-dimensional space, where its position on every single axis is its own random variable. Okay, this right here, this is where Gaussian distributions have a true superpower. In statistics, saying two things are uncorrelated is not the same as saying they're independent. For instance, your height and your favorite color are uncorrelated. There's no direct relationship. They're also independent. Knowing one tells me nothing about the other. For most data, that link isn't guaranteed. But for Gaussians, if two things are uncorrelated, they are, without a doubt, 100% independent. And trust me, that is a huge deal. For pretty much any other kind of random data, two things can be uncorrelated but still have some weird hidden connection. But Gaussians, they're clean. If there's no correlation, there's just no connection. Period. That simplicity is an incredibly powerful tool for scientists, and it's a huge piece of our puzzle. On to Section 3, where we uncover another one of these superpowers, the Gaussian's amazing stability. This property is another massive clue as to why it's so dominant in our world. So check this out. It's super simple. Imagine you grab one random number that comes from a bell curve. Then you go and grab a second random number from a totally different, totally independent bell curve. So what do you think happens when you just add them together? You might expect some weird, lumpy, complicated new shape to appear, right? But the result is another perfect bell curve. It's just a new one. This is called the stability property. No matter how many independent Gaussians you add up, you always get another Gaussian. It just doesn't break. And that is a massive clue in our investigation. And that clue leads us straight to the climax of our story in Section 4, the central limit theorem. This is it, folks. This is the big one. This is the core reason the bell curve shows up literally everywhere. Okay, so we know adding bell curves gives you another bell curve. Fair enough. But what happens if you add up a bunch of random things that have absolutely nothing to do with a bell curve to begin with? Let's just do a quick thought experiment. If you roll a single die, any number from 1 to 6 has the exact same probability, right? The distribution is totally flat. There's not a bell curve in sight. But now let's roll 2 dice and add their values together. Suddenly, things aren't flat anymore. Getting a 7 is way more likely than getting a 2 or a 12. See that?
It's already starting to build a little peak right in the middle. And this is where the magic happens. When we sum the results of 3 dice, or 5, or 20, the more independent random things we add together, the more the combined result starts to look exactly like that classic bell curve. It's like there's some kind of statistical gravity just pulling all these different random outcomes toward one single universal shape. This incredible phenomenon is the central limit theorem. What it says is that the sum of a whole bunch of independent random variables will always start to look like a Gaussian distribution. And here's the kicker, the really mind-blowing part. It works regardless of what the original distributions looked like. The source of the randomness doesn't matter one bit.
So let's bring it all home in our final section, the universal blueprint. This is where we get to see why this abstract mathematical idea actually matters in the real world.
So the crucial point, the profound implication here, is that this isn't just about dice rolls or equations on a chalkboard. The central limit theorem is basically the blueprint for how randomness actually behaves out in the wild.
The reason the bell curve is so universal is because so many things we see are just the sum total of a ton of tiny independent factors. I mean, think about a person's height. It's not one thing, right? It's the sum of countless genetic factors, nutritional factors, environmental factors, all added together. Same goes for tiny errors in a lab measurement. They're just the sum of many small disturbances. The central limit theorem basically guarantees that when you add up all that randomness, the bell curve is the pattern that's going to emerge.
And that leaves us with a final, fascinating question to think about. If all the chaos from countless, tiny, random events ultimately averages out into such a simple, predictable, and elegant pattern, what does that tell us about the real nature of chance and about the hidden order that might be lurking just beneath the surface of our universe?